Today we have a fascinating question from the Korean SAT. It's the 21st question from the 2018 September mock SCAR type paper, which is taken by STEM students. This question had a correct response rate of 39%, but since it's multiple choice, I think the actual difficulty is much higher. So have a read and have a go yourself. Pause the video now, and then we'll go through the solution after. So we can divide this question into two parts. So in the first part, we want to focus on the function itself. And the second part is looking at this integral. So before we do anything, let's start by drawing the graph of f of x to visualize it. First, we can start off by writing the first few terms of the sequence a of n. So of course, when a is 1, it's already defined to be -1. And then once we go to a of 2, we can use this equation here. So a of 2 is equal to 2 minus 1 over 2, 0. Yep. A of 3 is equal to 2 minus 1 over 2, 1. A of 4 is equal to 2 minus 1 over 2, 2. And this will keep on going. So if we want to rewrite this, this is the same as saying 2 minus 1, 2 minus half, 2 minus quarter. Now let's use this to figure out what f of x looks like for the various intervals that x lies in, where it says here, we can see that x lies between a of n and a of n plus 1. So, and we'll also list the period for each interval, so that it makes it easier for us to draw. Okay, so when n is equal to 1, f of x is equal to sine 2 pi x, and x lies between -1 and 1. So this is a of 1, a of 2. When n is equal to 2, sine 4 pi x, it's between a of 2 and a of 3. So that's just 1 and 3 on 2. And let's do another one. When n is equal to 3, sine 8 pi x, and it's between a of 3 and a of 4, which is between 3 over 2 and 7 over 4. Now we want to find the period of each function, and note that for the general function sine bx, the period is 2 pi on b. So if we use this formula for each of these intervals, when the function is sine 2 pi x, when the function is sine of 2 pi x, the period is 2 pi on 2 pi, so the period is 1. When n is equal to 2, so sine 4 pi x, the period is 2 pi on 4 pi, which is 1 on 2. When n is equal to 3, so sine 8 pi x, the period is 2 pi on 8 pi, which is equal to a quarter. So now using this information, we can draw the graph like so. So we can start by labeling each of our intervals. So first, when n is equal to 1, a of 1 would be at -1. So let's label that a of 1. And that will finish at 1. So this is 1, which is also a of 2. And then so this will mean 2 is here. So a of 3 would be 1.5, which is here. So 3 on 2, or a of 3. And then we can keep going. You could see that the interval halves each time, except for when it is between a of 1 and a of 2. When n equals 1, the period of the function is 1. So we can draw a sine wave like that. And since it goes from -1 to 1, we actually make another period like this. So this is when n is equal to 1. So when n is equal to 2, the period is a half, which is exactly the size of this interval. So we can draw it like so. When n is equal to 3, the period is a quarter, which is again like so. And you can imagine this just goes on forever. So I think now that we have a general idea of this function, we can move on to this next part. We now have the tools to move on to the next section of the question. So that's this section. So we're talking about this integral here. So I'll rewrite that down here. We have the integral from alpha to t, f of x dx equals 0. So we'll just focus on the integral here and don't worry about alpha, t, and 103 just for now. So having two unknown bounds is a bit confusing. So we can use a property of the integral to write this as so. Alpha to 0, f of x dx plus 0 to t, f of x dx equals 0. And of course we can rearrange this to give. We can arrange this to give the integral from 0 to t f of x dx is equal to the negative integral from alpha to 0 f of x dx. And the reason why we can split it like this is if we look at the upper and lower bounds of alpha and t spans from 0 to 2 and alpha is from -1 to 0. So that means the upper bound of alpha is 0 and the lower bound of t is 0. So we can use 0 as our, I guess we can call it the middle point. Using the bounds of alpha and t, since alpha goes from -1 to 0 and t goes from 0 to 2, we can think of alpha as somewhere here and we can think of t as somewhere here. So we don't really know what alpha or t is, but we can think of it as alpha being on the left side of the y-axis and t being on the right side of the y-axis. So if we look at these two integrals, we can find that this integral will be a constant. So if we set alpha to some number, for example here, this area that we get, or the integral from alpha to 0, will be a constant. So since we set this to some constant k represents the area under function f of x from alpha to 0. And on the left hand side, since this integral changes depending on t, we can set this to a function g of t. So in other words, g of t is a function that tells us how the area of the function from 0 to t changes as t changes. Now let's draw a rough graph of these two functions, g of t and constant k, on a new axis. For now, let's focus on the positive side of the y-axis. And we can see that we'll just set k as some arbitrary number. So we can just say this is k, y is equal to k. And we can now look at how the area under the graph changes as we change t. So we'll just follow the path of this graph. So if we start at 0, as it goes up, the area goes up, 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 and it goes down, 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 down. So if the function makes a full period, then the overall area is going to be 0. So in other words, if t was 1, then the integral from 0 to 1 or 0 to t would be 0. And it's the same here. The area would go up, 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 down, 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 and then it'll be 0. And that will just keep continuing. So if we think of this function, g of t, as a function of the area under the curve as we change t, we'll label a of 2 here and a of 3. We'll label all of the intercepts. So the area would go up, 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 then down, 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 down. So it's made one period, but the area itself, it's gone up then down. And again, this time we can see that the overall area from A2 to A3 would be smaller. So let's draw this hill smaller. So from A to A3, we'll go up, 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 down, 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 down. Same thing, up, 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 down, 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 up, 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 down, down, down. And this is just going to continue forever. So if we go back to the question tells us that the number of t that satisfy this equation that we have, well, we've changed it a little bit, but it's the same thing. The number of t that satisfy this equation is 103. So let's unpack that a little bit. First, we'll move back to our original graph. So our original graph is here. So I'll just write here number t is 103. Okay, so for example, if alpha was here, let's set alpha to be here. Then we want to set t such that the area of both sides of the y-axis is equal. With half of this and then a full of this, we're going to end up with that much. So if we want to undo this on the other side, so it'll be like this and then this. So you can see that the symmetry here is that the area on both sides are equal. So this would be one value of t that would satisfy this. Then similarly, we can do another cycle and this another t might satisfy this, and so on and so on and so on. So that's how we could think of it in the original graph. But right now it's a bit abstract and it's a bit hard to understand, and you might not know how we can solve this mathematically. So that's where our second graph comes in. So if we transpose this idea to our second graph here, since we want the integral from alpha to 0 and 0 to t equal, the number of t that satisfy this is the same as considering the number of intersections between the two functions. So since we've set the integral from alpha to 0 and the integral from 0 to t as a function, if we want those two to be equal, it's the same as saying that there are some number of intersections between the two. So for example, if we set alpha to be something here, then the number of intersections in our second graph would be 1, 2, 3, 4. So that's 4 intersections, right? So we have 4 intersections, but we actually want 103. So feel free to pause the video here and wrap your head around this idea. So now we have a much nicer way, a much more practical way of looking at this problem. So we want to find out how can we get 103 intersections between these two functions, g of t and k. So notice that if k cuts through g of t, we get 2 intersections at every hill. But we actually want 103, which is an odd number. Know that the last one must be just touching the maximum of one of these hills. We could have it so that it's just touching this last one. It's touching this last one. So then now we have 1, 2, 3, 4, 5 intersections. So we have an odd number, so this is what we want. So what we could do is we could rewrite 103 as 51 lots of 2, so 51 pairs, plus 1 extra. So this means that we are cutting through 51 hills, and the last one will just be touching the maximum. So if we look at the pattern of how the number of intersections correlate to the intercepts in terms of a of n, we can see that, so let's look at this second graph. If we have 2 intersections here, it's a of 2. We make another one, so we have 4, a of 3, and then we have, if this cut through the last 2, we would have 6, right? So we can think of this as doubling the previous intersection. So we get 4 by multiplying n equals 2, 6 by multiplying n equals 3. So if we want 51, we want to go all the way to a of 51, and then we want to touch the last one. So we would have, and it will just be cutting through all of them, and this last one will lie between a of 52 and a of 53. So what does this actually mean for our first graph? So we're going back to our first graph, since this will actually give us the area. The actual question here, so the final question, is to find the value of log base 2 of 1 minus cosine 2 pi alpha. So this means that we actually want to find something in terms of the value alpha. So if we look at f of x from 0 to this midpoint of a of 52 and a of 53, let's call this m. Let's say we have another one here, and it's a of 52, a of 53, and we want to go up to this middle bit. So this is m. Then as we go and go and go and go on, every single time it goes through one period, it's going to be 0. So 0, 0, 0, etc., etc. And then we're just left with this tiny, tiny little section. So everything before that is 0. So this means that the overall area from 0 to A52 is just 0. The net area is actually 0, except for this tiny portion here. So instead of computing the integral from A52 to A53, so if we wanted to do that, we would have to substitute n equals 52 into the sequence, and then we'll get a big number, and it'll be really annoying to solve. So instead of doing that, we can just look at this function by itself and move that to the origin. Since everything before that is irrelevant, it all cancels to be 0, we can just look at this last bit. So if I make that a bit bigger, and remember we just want to look at this bit. We just want to look at the area of this first half. So we're going from 0 to somewhere here. N is equal to 52, which means the function is y equals sine of 252 pi x. So what's the period? The period is 2 pi on 2 to the power 52 pi. So pi cancels, and we are left with 1 over 2 to the power of 51. So that means in this little bit that we've drawn here, it's going from 0 to 1 over 2 to the power 51. And since we're looking at this little bit here, the first half, we just find the midpoint between the two. And so if we divide 1 over 2 to the power 51 by 2, we get 1 over 2 to the power of 52. So that means we are interested in looking at the integral of this function from 0 to 1 over 2 to the power 52. So let's write that. We want to find the integral from 0 to 1 over 2 to the power 52 of this function, sine of 2 to the power 52 pi x dx. So it will be negative 1 over 2 over 52 pi cosine 2 over 52 pi x. And that's going from 1 over 2 to the power 52 to 0. Since this is a constant, we'll take that out. We can get cosine 252 pi 1 over 252 minus cosine 252 pi 0. And this will be equal to cosine pi minus cosine 0. Cosine pi is equal to negative 1. Cosine 0 is equal to positive 1. So together that makes negative 2. So if we expand this, negative cancel, we'll get 2 over 2 to the power 52 pi, which is equal to 1 over 2 to the power 51 pi. So what is this actually? We look at the right hand side. So this is actually g of t, isn't it? But in fact, g of t is equal to k. So we can say that this is equal to g of t, which is equal to k. And what is k? K is equal to the negative integral from alpha to 0 of f of x dx. So we can equivocate this number with this integral. So let's first start by simplifying this. We have the negative integral from alpha to 0 sine 2n pi x dx. But actually in the graph, wherever alpha lies, n will always be equal to 1. Since n equals 1 goes from a of 1, which is negative 1, all the way to 1. So we can actually get rid of the n here. N is actually 2 to the power of 1, which is just 2. So now we have this, and we can rewrite this as, we'll keep the negative outside, will be 1 over 2 pi negative cosine 2 pi x from alpha to 0. And so negative cancel. So this is equal to 1 over 2 pi cosine 0 minus 1 over 2 pi cosine 2 pi alpha. And let's factorize 1 over 2 pi. So we have 1 over 2 pi. Cosine 0 is 1. So this will be 1 minus cosine 2 pi alpha. And remember this integral is equal to 1 over 2 over to the power 51 pi. So let's put the equal here. This is equal to 1 over 2 to the power 51 pi. I think this looks a bit familiar. Let's see why. So we actually want to find log base 2 of 1 minus cosine 2 pi alpha. And that's exactly what we have here. And so let's just find this on its own. We can divide 1 over 2 pi on both sides. So we will get 1 minus cosine 2 pi alpha equals 2 pi over 2 to the power 51 pi. Cancel, cancel. This is equal to 1 over 2 to the power 50. Notice that 1 over 2 to the power 50, we can write that as 2 to the power of negative 50. So this logarithm here, that is simply log base 2 of 2 to the power of negative 50, which is equal to negative 50. And there we have our answer.